once we get this up and running. So that was interesting, interesting approach. At Deco, we have a slightly different take. Instead of avoiding the actual tracking problem, we developed a strategy to solve it. I'm going to show you how. All right. I need help on this. There we go. All right. Yeah, welcome. Thanks for coming. Today we would like to share with you what we achieved from using a technique called hybrid tracking on consumer mobile devices. In technology, hybrid means the combination of two or more technologies to improve the solution of a specific problem. And usually each of those technologies you pick is a solution to the problem by itself, but it is smart combination that makes the whole more than the sum of its parts. Let me give you an example. What do you think, how far away is that tree? Well, I mean, there are several ways to figure out. First of all, you might just want to have a quick look and a quick guess.
20 meters, maybe.
20 meters. Though you might also just, want to walk over, count your steps, and get a bit of a more precise understanding of the actual distance, and might conclude like
25 meters.
And the real distance might be 24, something like that. So each of those methods you use to measure the distance has its own weaknesses and strengths, obviously. I mean, looking at it is really fast, really quick. It's rather inaccurate. Walking over takes a bit more time. It's more accurate. The trick is in the smart combination of the different methods you use, and to compensate the one method's weaknesses with the other method's strengths to get an overall great system performance. That's the fundamental idea of hybrid systems. We want to be fast and precise. At Deco, we applied this technique to solve the weaknesses of today's single-camera tracking systems on mobile devices. Problem number one, resources. Pure image processing is just terribly expensive. Problem number two, usability. Current optical trackers have only a limited support for fast device motion. And problem number three, scale. We want to augment the real world in real world size. These are the three problems we address with hybrid tracking.
All right. Good day. So actually, originally Marc was scheduled to talk by himself, but since we have this hybrid word in the title, we decided to mix this presentation a little bit and give it.
And we leave it up to you to figure out our individual weaknesses and strengths and how we compensate for them.
So anyway, I'll show now how we addressing all these three problems at DECA, and we'll start from the first one, which we call image processing is too expensive. So what people do, they say, okay, forget about natural features, let's track artificial markers. Well, in fact, if you look into timeline, it was happening different ways. So whatever you see here, those markers are circa 2001, roughly speaking. So, and since that, people were using markers all the time, and most of solutions are still marker-based. But if you look into mobile applications, and if you look into your phone, how many applications on your phone require something else to carry around in your pocket in addition to mobile phone itself? Well, I don't have any on my phone, so if anybody can mention anything, that's great. So that's not really a solution to go back to markers. The second solution, okay, if we use features, we can have less features. Less features meaning less tracking accuracy, also not good. And the last one, well, we can still have many features and go for slower frame rate, get very stable tracking locally, but since it's very low rate, jitter and latency starting to appear for the user, and it leads to bad user experience. So, well, our solution is to utilize the plurality of sensors available on majority of modern mobile devices. So I probably did not list all of them here, but would like briefly touch three groups. The first one is what people call motion sensors, and they provide a relative pose of the device in 6 coordinates, but this is only orientation-wise involved coordinate system, because motion sensors do not know where you are. So GPS, it's a little bit different. It knows where you are, but, well, it's very badly knows where you are. And it's only 3D pose, giving you only position and not orientation. And finally, the main sensor or tool that people are using is cameras. And cameras give all 6 degrees of freedom, but in local world coordinate system, because camera doesn't know if I'm here in Santa Clara or in Boston, from where I am.
The sense of fusion takes the best of all worlds. It picks basically the raisins of all the inputs we have. That's the idea of the sense of fusion core.
Right. That's why it's shown different color. Okay. So the problem number 2, on purely optical single camera system, it's very limited support of fast device motion. So I was figuring out what a solution, and we found 2. The first one is do not move fast. The second one, well, once again goes back to markerless system. If you are able to keep marker in your field of view at any time, well, you can go faster, but then you have to have many markers for this. So what we do, we, well, combine the best from 2 things. A high accuracy video, which is low frequency, unfortunately, and high frequency motion sensors input, which is low accuracy. So, and the diagram shown below is basically the green stuff is good video frames. So what's happened, user takes a device and moves fast. So the red one is optical frames that there is nothing to extract from, so they lost.
Because they're blurry, right? Quick, they get blurry.
Yeah, or you can occlude the camera if you like in addition to that. But yeah, that's what's happened. And so then motion sensors, they much higher frequency, but smaller accuracy. That's why they're shown in small size here. And we merge 2 systems together, we can get a hybrid output of good tracking quality at least video rate or higher, if you like. And the last problem is we would like to augment the world in real world size or real scale. And the solution, once again, is to place a known object in a scene, which is marker, and if you measure it before and you know what is the size, once you recognize it, okay, you don't have scale problem. Second, you put a super precise alternative sensor, which is not available on mobile device, but, well, it's external hardware solution. And the third method is basically you capture the scene and then you dial on your device, well, okay, the distance to that tree is 25 meters, the size of the tree, the height is 10 meters, let's put 10. Okay, now I'm more or less in real world scale.
That's not exactly a great user experience. So.
Well, if you dial fast, it could be fine. But anyway, yeah, it's not exactly good. And so what we do, we basically utilized a well-known principle of triangulation. Like suppose we have two cameras and they rigidly attached one to each other, then you can triangulate the same feature and find the distance to this feature very easy. On mobile device, so far, we don't have two cameras available. So what we do, we basically build what we call a synthetic stereo pair, where one image is treated as one camera and another image is treated as another camera. And if you can figure out time and space correspondence between these two cameras, you pretty much could triangulate and find the distance and the size to the feature. And I guess...
So cool. So these are basically the free solution to the free problems we identified in today's single camera optical tracking systems. But what do we do with this now? So why do we do this? Well, we do 3D reconstruction, we do occlusion, and we do collision. We basically take the scene in front of you and reconstruct it in 3D on the fly. And so we can occlude the augmentation with real-world objects, and the real and the virtual objects literally collide. And we do this on a consumer mobile device. Let's have a look. It bumps into the box, it jumps on top of the box, it runs behind the box. With this, we enable a whole universe of new applications that go far beyond anything that we've seen in the mobile AI space before. So summing it up, we solved the weaknesses of today's single camera optical tracking systems, the resources problem, the usability problem, the scale, and we use our own patented technology for that. We do 3D reconstruction, occlusion, and collision on a consumer mobile device, and all be available in a Deco SDK, registered today at developer.deco.co. Plus, there will be more from Deco on this year's ARE, talk from our CEO, our product designer, and principal engineer all tomorrow. Enjoy the rest of the conference. Thanks for coming. Certainly open for questions, of course.
Yes, so questions, and while questions, if Ben can come up and we can get him ready, the next speaker, that would be great.
Questions?
Very interesting talk. I have two questions. First, you mentioned the synthetic stereo camera. I know you have this patented technology, but can you say something that you can say? Because when you have only single mobile camera, you don't really know the relative position between your current frame and the previous frame. And you know, stereo camera is very tricky.
Well, I can say a little bit. Let's say you took a picture from here, you moved here, and you know how this location corresponds to this one. Then you basically can triangulate and treat it as a stereo pair. Of course, you have to know also the time difference and compensate for that, but that's the idea. To learn more, if you come in a break, I maybe can tell more about that.
Sure. Yeah, the second thing is in your demo is very interesting. I think you're trying to show that the virtual object can kind of run behind the true object.
Right.
But what I noticed that the depth of that paper box is not perfect. So your object run into that. I think that's probably because of the depth map. So is this the, well, I know this is more a little bit harsh question. Is this the best you can get from this paper box?
No, it's not the best we can get from this paper
Okay,
box. We
because
can get better.
otherwise what I mean is that if you can really get the true object 3D shape of that box, then you could render the virtual object really behind the box, not into it.
Yeah, I mean, you could have seen it picked up the top of the box as well. So it did actually get the 3D shape right. It didn't like exactly pixel-wise match it though. But that's doable as well, of course, yeah.
Okay, thank you.
I would like to add, whatever you saw here, it was the sequence shot right away, so there were no preliminary study of the scene. So if you extend your experience for a little bit longer, it will eventually get entire box to be right. So
Okay, all right, thank you.
Hello. With your technology, could you recreate and extract a 3D model of a textured object by just turning around? So you have an object on a desk, and then you turn around with the camera and recreate the object.
Yep.
So
we reconstruct an arbitrary scene.
And can we, after that, get to the triangles to display the object elsewhere?
I didn't understand that.
Can you extract it as a 3D model that we can use elsewhere?
Well, that's a pretty technical question. Guess we should dive into that like after the talk. But yeah, interesting question.
How you doing? How low do you go? What's the lower processing end? Like, do you need a phone with a 1.2 megahertz processor for this? A 600 megahertz? Would that work?
We start from iPhone 4S.
800.
Cool.
Any more questions?
Touch on your business model a little bit. I went to the website, but I mean, your products are testing now. When can I get one, or how do we get to the developer community?
So when it comes to business models, you might want to talk to our CEO in the back, Matt Meisnix.
Okay.
Yep.
Thank you.
He's happy to chat.
Hi, Landon. I just have two questions. One, what frame rate were you running at for the iPhone? The example you had on there.
Well, at iPhone, video is running at 30 frames per second, so that's more or less what you see here.
And you were doing the processing on the phone?
Yes.
Yeah. And then I guess the second question is, for the sensor fusion approach, you know, together with the stereo model, are there other sensors that you would want that would improve the sensor fusion process?
Well, I would like to get 5 cameras and rangefinders, then it will be better.
Yeah.
But whatever I have is probably good enough for whatever we're doing.
Yeah, thanks.
When you guys talk about the sensor fusion module that you've built, is that actually running? That, you know, there are other sensor fusion modules that are running on platforms today, right? Are you an add-on to one of those? Or are you running next to one of those? I mean, where do those algos sit architecturally?
What are the other platforms you referring?
Well, if you look at some of the platforms coming out on the way Microsoft's supporting sensors, there's support for sensor fusion modules and capabilities in that platform, right? There's companies like InvenSense that are doing, that I think is a speaker, that are doing sensor fusion modules, right? Those kinds of things, right? Are you looking to have your algos run in those, you know, in those sensor fusion platforms, or are you next to them? Or I'm just trying to get a sense of Marc said.
Well, this is iPhone and iPad, so they don't know what Microsoft is. As for InvenSense, it's manufacturer of inertial sensors, and I guess different company has sensors in Apple devices. So we are not using anybody else
This is
architecture.
our own proprietary technology.
Yeah, no, I understand that. I guess I'll ask it, and then I'll give up. I'm trying to get a sense of where it sits on the platform. Is it running on a sensor fusion?
Yep.
Yeah.
I see.
I could have a shot at answering that.
Yep.
I mean, sensor fusion is a generic term, meaning sensors fused together. InvenSense are fusing inertial sensors to produce some inertial output. Apple's core motion APIs do pretty crude sensor fusion of inertial sensors. Our sensor fusion fuses optical and inertial to pose tracking of the camera. As far as we know, we're the only people who've ever done that, definitely on a mobile device. If a subsystem like the inertial systems, like we know InvenSense, and we're looking forward to working with them to get their fused inertial sensors, and that makes our job a lot easier because we effectively have to rewrite Apple's core motion APIs to take the raw data because their fusion software just wasn't good enough to give the results.
Is it true you think you're the first to use optical together with inertial sensors?
Leonard was the co-inventor of this technology 2 years ago, and as far as we know, we're the first people to do it on a consumer mobile platform. We're definitely not the first people to do it full stop, but doing an inertial pose with an optical pose, fusing that together for a tracking system. If anyone's done it, come talk to us, I'll hire you.
And last question.
So you mentioned that the existing scale estimation approaches have, accuracy only up to like 3 millimeters or so. So what is the estimation accuracy with your system?
In scale?
Yes.
Well, that depends on various factors. For example, the longer you play, the better it becomes. We did not do rigorous testing yet, so I cannot say anything specific at the moment.
One last question. Does the performance has any relation with respect to the depth, like depth of the scene? Will it get affected if you?
Yeah, of course. If the depth is very big, then when you triangulate, your angle is very narrow, and you get in standard problem of dilution of precision. So it's like in any system. So.
There we go.
Well, gentlemen, thank you for the presentation and the time.